So let us work on this problem that we are given that number of drops from an eye drop medication show a normal distribution from each bottle with a mean of 65 drops and a standard deviation of 2.4 drops. Now what we want to know is that what is the percentage of bottles that will dispense less than 62 drops. That is first we will calculate this area under the normal curve and then change it to percentage. So what we shall do is this. Let's pull up our calculator. Okay, and most of the calculators have this feature. So we go to normal cumulative distribution function. All right, lower, we don't have any lower bound, so we just leave it as it is. And then we have 62, 65 is the mean, and 2.4 is the standard deviation. And once we do that, we get 0.1056 as this area. Now notice one thing. It looks a little awkward to put negative infinity as contents of bottle. So in this case, you can see the mean is 65, standard deviation is 2.4. So even if, just to accommodate practical situation, even if you put the lowest value as 0, you will get the same answer here in this particular situation. All right, so what we got is that this area here is how much? This area here is simply 0.1056, and which means that 10.54% of the bottles would dispense as 62 or lesser number of drops. All right, now let's see this here, that say we are, or say a patient is receiving a set of 4 bottles in every supply. All right, so some of them will have less amount, some of them will have more amount. So let's see how the averages vary. All right, now before we go ahead, let me just clarify one point, that this is not really negative infinity. I don't know what that is. This is simply the smallest number that the calculator could handle in my knowledge. All right, so assuming that a patient gets a set of 4 bottles for 4 months supply at a time, what we are going to do is that going to simulate the contents of random samples of size 4 by using software called Minitab that's available to you from the college. And let's just take, say, 10,000 such samples of size 4. Okay, or in other words, what we are doing is that, or what we are doing actually for the purpose of that simulation is that we are just going to go ahead, take a normal distribution with mean of 65 units and a standard deviation of 2.4 units. Okay, and take how many? 10,000 such samples of size 4. All right, so in Minitab, I'm going to calc, and then I'm going to ask it to give me random data, and then we are taking getting the random data from a normal distribution. And what we would do is that we are going to get 10,000 such samples, and the samples are in rows 1 through 4, and the mean is 65 and standard deviation is 2.4. So let's go ahead and look at those 10,000 samples. So here they are. All right, so what we mean by this is this, that here we have the first sample of size 4, then the second sample of size 4, and then go on in this manner. So what we meant was that each row will give us the contents on the inset of 4 bottles, and we have 10,000 such samples. So let's go ahead and look at the mean contents of each sample, going back to Minitab. So now I'm back here and going back to calc and looking at row statistics. And what do I mean is that I want the means, okay, of each row of the first 4 columns, and we are going to put the results in the column 5. So here they are. So here are the means of each of those samples as they go in order here in the order that we have placed them. So I brought these numbers from that Minitab worksheet, that X bar, that's our symbol for sample mean. So we can see that we got all these sample means here. Forgive my handwriting. All right. So these are the mean number of drops for each sample. And just for interest, I mean, we may note that we have 16 observations here and only one is showing contents of less than 62 drops. All right. So let's see that how many of these 10,000 samples of size 4 show an average value of less than 62 drops. All right. So let's go ahead and we are going to just put this column of means sorted into this one just to read the number of samples that have mean contents of less than 62. Okay. So let's go to calc. All right. And then we are going to go to calculator and we want to put in C6. Okay. And what do we want to put in there is the values in the C5 sorted. All right. So here they are, and we can now notice that the number of samples with contents of less than 62 drops is how much? How many? 61 out of 10,000. So what we found is this, that 61 out of 10,000, okay, which is how much? 0.0061. You know, that's the proportion of samples that will have a content, mean content X bar, okay, of less than 62 drops, right? Or the probability is 0.0061 or such percentage is 0.61%, okay, which is much lower than 10.56% that we had. Now let's go ahead and see how does this distribution look like, okay? So I'm going to make a histogram. So first I would do this. Let's get some, you know, space to make the histogram, and we shall make the histogram of the mean number of drops, okay? And so here is histogram. We will get a simple one, and here is the mean number of drops, okay? And say okay, and here is a histogram, and this distribution is also, you may see, is approximately normal. And if we look at its descriptive statistics again for the mean, let's see what that comes out to be. So here the mean is again about 0.65, right? Let me just take it in another box for you. And the standard deviation is how much? 1.192, which you may round to 1.2. So let me bring it in a new window and talk about it. So here are the distributions of X bars, the sample means, and the mean of the sample means is about 65 if we round it, 65 drops. Of course, we have 10,000 samples out of lot, you know, many more that are possible. And the standard deviation is what? 1.19 or about 1.2, okay? So when we took the samples of size 4, what it did was that it cut down the variability, this measure of variability or dispersion or deviation into half, because the original had what? The mean was the same, but the standard deviation was 2.4, okay? So now we are going to just write a working result that we shall take up in our next class. So here what we have is that if we take simple random samples of size n from a population that has a mean mu and a standard deviation sigma, then the sample means that we denote by x bar will also show a mean of mu, but the standard deviation will be lower. And note an additional point that for this to happen, we need the population to be lot larger than the sample size. So for example, in our case that we just saw, remember this, our sample size was 4, right? And of course there are many millions of bottles for such patients, right? And the mean mu was 65 units, sigma was 2.4 units. So when we looked at the distribution of x bars, we saw that the mean, of course, it stays as 65 units, but the standard deviation just gets reduced by what? A factor of 1 over square root of n, and actually by this we mean 2.4, and here is 4, so that's 2.4 over 2, that is 1.2. Now other important points to note are these, that is, if the, let me just write it down, if the population has a normal distribution, okay, then sample means x bars will also have normal distribution, okay? So will also, let me not rush, have normal distribution, okay? And even if the population does not have a normal distribution, that is, so let me first erase this to get some space to write. Okay, so here we are. So what I wanted to say was this, that even if the population does not have a normal distribution, okay, these sample means will still show a normal distribution. By sample means we mean, you know, our x bars, okay, for large sample size, okay, and we will state how large it has to be. And this is a very celebrated result that we shall use, and it's called the central limit theorem. All right, so we shall continue with the calculations based on this statement in our future sessions.